Hi, everyone. Thank you very much for coming. I wanted to take this opportunity, this track was the future of networking, to answer a couple of questions that I often get asked. The first is, what comes after SD-WAN? And the second is, what is the relationship between SD-WAN and NFV? Are they the same thing? Are they different things? Are they friends or are they enemies? So let's get started with that first question. What comes after SD-WAN? This is a question I get asked a lot. In fact, a couple of years ago, I was asked about this by my own engineering team. And so I showed them this slide. This is what comes after SD-WAN. And they thought, what? I know we see those every day in Mountain View, a Google self-driving car. Is David thinking that the next thing we do is build self-driving cars? No. What I said was after SD-WAN was SD-WAN. Of course, this is a play on words, but in a sense, I think the future is about going from this SD being software-defined, the software-defined WAN, to SD meaning self-driving, the self-driving WAN, a WAN that reacts and looks after itself, a WAN where you can drive it by intent. And so I want to talk today about 4 ways that we are using AI and machine learning today to drive us down this path towards the self-driving WAN. But before I go there, I want to answer another question I often get asked, which is why is SD-WAN called software-defined WAN? And I don't know who first coined the term, but the way that I explain this is by thinking about it in terms of the software-defined data center. As most of you know, the idea of a software-defined data center is to be able to run any application on any server. And in order to do that, there's this layer of virtualization using hypervisors and orchestration that makes that pool of servers, which can be mixed and matched from different vendors, that can be upgraded independently of your applications. Applications just keep running. That hypervisor and orchestration, that layer, is what really lets you treat it as an agile pool of server resources, any app on any server. If you take that idea and apply it to networking, you get SD-WAN. The idea is instead of trying to run any app on any server, we're trying to be able to run any app over any transport or any combination of transports. And to do that, instead of having a hypervisor and orchestration, we've got an overlay, a virtual overlay or bonded overlay and orchestration to treat those transports as a pool with which I can take an app and a given set of quality objectives and map them onto those underlying transports to deliver what the application needs. So that's how I think about SD-WAN and why SD-WAN is called software-defined WAN. It's really a twist on what's going on in the software-defined data center. So back to the self-driving WAN. As I said, I want to talk about 4 ways that we are using AI and machine learning today to give you a little bit of a taste of where things are going. A lot of people talk about AI, they talk about machine learning as if it's way in the future and as if it's a vision. And certainly, there is a long way to go and a lot we can do going forwards, but it is actually something that we are using today. So the first thing about this particular Google car is when it was brought to market by Google, when they first started launching it, it had no steering wheel, no brake, no accelerator, no dashboard, no instruments, just a voice control and an emergency stop button. Now, the California DMV wouldn't let it on the road without a steering wheel, so eventually they did put in a steering wheel. But the idea of the self-driving car is this intent-based system. You say, I want to go to the supermarket, I want to take me to the airport, I want to go to the hotel. You tell it where you want to go, and everything else just happens. You don't need an airplane cockpit full of instruments and knobs to get from A to B. And so I think the first thing we need to do in networking is move to that level where we're capturing intent rather than trying to describe what we want to do in excruciating detail. Another way of thinking about this is with the CIO today in an enterprise. He has an idea of what he wants his network to do. I want my voice calls to be carried with high quality. I want no call drops. I want my VDI sessions in my branches to be glitch-free. I don't want those screens freezing. I want my backups to finish by 3 a.m. on Sunday morning. Whatever it may be, he has these high-level goals. He expresses this to the networking team, a team of CCIEs. They develop a network architecture to deliver on those goals or modify their existing architecture. And then they translate that architecture into thousands of lines of CLI that then get adapted for each and every site. It's very manual. It's the way it's been done for 30 years. It's probably time to think about doing it differently. One of the things that has happened in the last few years is people have begun to apply DevOps techniques, scripting and automation to help simplify the problem. But for most enterprises, they don't have a big DevOps team. And what's more, scripting and automation really only cope with the anticipated cases, things like turning up a new branch. It's not good for dealing with unanticipated things. And as you all know, the WAN is full of surprises. So where we want to get with SD-WAN is to an intent-based system where we capture that intent from the CIO or the business unit leader in one screen, in one place, which describes what he wants the network to do for a particular class of applications. And then have that orchestrator work in conjunction with all of the edge devices to just make that happen, with no human ever being involved in configuring or thinking about individual elements. And to me, this is what the self-driving WAN is all about. Where are we today? I'm not going to go into a lot of detail, but this is a screenshot from our orchestrator. This one screen is, of course, our business intent overlay screen, where we capture what we want to do for a particular class of applications, like, say, voice or replication or VDI. And from here, everything else is driven. And so there's a lot more I could go into here, but I just want to tell you that we have been working on this, and we have this intent-based system, and I believe this is where we need to go to, the path we need to be on going forwards. Another thing that a self-driving car has to deal with is bumps in the road, unanticipated things going on, pedestrians running out in front of you. Same thing in a WAN. We've got to be able to deal with unanticipated consequences. Things like packet loss and latency, brownouts, and so on. One of the things that we do in our SD-WAN is use fault error correction or erasure coding, something that you guys from optical networking or even in copper-based networking use all the time at the bit level. We do that at the network level so that as we send data over the network, we use multiple paths in parallel, like MIMO and wireless, and we use a layer of erasure coding or fault error correction, so that even if packets are being dropped on all of the links, we're still able to deliver the packets to the end user without any missing packets. And in essence, it's a way of doing synthetic QoS, so that you can give end-to-end QoS, which is better than any of the underlying paths. And so this is something where there's an overhead involved in doing it. And where we've applied machine learning is in adapting the amount of error correction overhead we use on each path in response to what we've measured in the recent past. And so in order to kind of be able to be on the right place in terms of how much overhead do I add and how much quality of service do I deliver, we use machine learning. So from a graphical point of view, over on the right, you can see two underlay links, an MPLS link and an internet link. The orange indicates when those links by themselves wouldn't be meeting the application's quality of service. At the top, you can see what's delivered on the overlay, which is by combining the two links and using fault error correction, we could deliver green perfect service to that particular app. So a third way that we're employing AI and machine learning is in anticipating the future, using a model based on a lot of data to be able to predict the future. And so one place we do this is in our application classification engine. As most of you know, traditional application classification uses ports, so like port 80 equals HTTP, or port 443 is HTTPS, and DPI, where you look inside multiple packets inside the flow to try and extract information and signatures that let you identify an application. While DPI is powerful, one of the problems with it is that you need to look at many, many packets before you can determine what an application is. And when you look at an SD-WAN and what it has to do, a lot of it is about steering traffic, deciding whether I break this traffic out locally or send it to a cloud service or send it to a data center. And when there's NAT in the path, it might not be evident at first, but when NAT's in the path, you have to make that decision on the very first packet of a flow. And so DPI can't give you a decision on the first packet of a flow. So we thought about, what about if we collected information about every single flow we'd seen? What about if we collected information about all the DNS requests and responses that were going through our box? And what about if we associated that with DPI decisions that we'd also made in the past so that we could build a model where when we get one packet say, a SYN packet for a connection that's going to go to Facebook. That SYN packet has nothing about Facebook in it. But we could use an AI model to predict that that packet is going to be a Facebook connection. That's what we've done. And we call it first packet IQ. So it's a way of using machine learning to augment traditional application classification to get a first packet decision. And what does that let us do? Well, it lets us do granular internet breakout. One of the challenges behind internet breakout in every branch is it's always been an all or nothing proposition. I either break everything out or I don't. But in fact, internet distant traffic comes in a variety of different flavors. There's your SaaS applications, so Salesforce, Marketo, NetSuite, Office 365. They're good things. And the CIO's intent for those is generally, I want those to work as reliably as possible, and I want the user's experience to be as good as possible. Then there's perhaps another category, which I like to call home from work instead of work from home. So that's people using Facebook and Yahoo Mail and hopefully not, but maybe Netflix and YouTube at work. And so maybe there's a different policy or intent for those. Perhaps it's not to block them, but perhaps it's to take them out, dump them off your network as quickly as you can, maybe to a cloud-based service like Zscaler to make sure it's scrubbed. And then there's another category, which is everything else. Traffic going to countries you don't do business in, or to websites where no one from your company should be visiting. Maybe for that, we want to take it to your data center and put it through a full security stack. So this is the kind of thing that we hear from enterprises in terms of what they want. And by doing first packet IQ, we're able to use that artificial intelligence to help steer the traffic the way that they want in an intent basis. The last example of using AI and machine learning is around turning data into insight and action. So in a typical enterprise's SD-WAN, they may have a few hundred sites. And if they're using several different transports, say MPLS, Internet, and LTE, they're going to have hundreds of thousands, in fact, in some cases, millions of individual paths between all of their devices. On each of those paths, in each packet, we have a sequence number and a timestamp. So every second, on millions of paths, we're measuring the latency, the loss, and the jitter of that path and saving all that information. Now, one of the things we realized early on is it's one thing to save it. You can then go back and on this link between, this path between here and here, last Wednesday from 1:05 to 1:10, what was going on? We have that, we can answer that question. But for humans, we're overwhelmed by all that information. How do we know where to look? And so one of the things we've done is implement what we call a health map, a way of using AI to consolidate data and also visualization to make it easier for a human to navigate. So the idea of our health map is you've got locations on the y-axis, time on the x-axis. Each dot represents 1 hour at a particular site, and then the classic green, orange, red kind of classification. You can drill down from there to understand why it's red. You can filter by, do you want to look at QoS events like jitter violations, or do you want to look at a more classic alarm view? But basically, it's the idea of being able to take those terabytes of data and make them human navigable. Now, this is only the tip of the iceberg. There's a long way to go in terms of being able to apply AI to this problem of navigating through huge amounts of data. In fact, I think there's a lot of application of tying this into the type of orchestration, the automated trouble ticketing things that the MEF does to help make the inference that we have from individual enterprises SD-WAN that something's wrong on a particular circuit to be able to have those trouble tickets opened automatically and basically make the network operator's job easier. Finally, I want to get to the other question that I asked at the beginning, which is how do NFV and SD-WAN relate to each other? So you remember that I talked about the software-defined WAN being like a hypervisor for the network. It basically makes the network virtualized. That's helpful when we kind of think about this question of SD-WAN and NFV. Are they best buddies or are they kind of frenemies? We all agree that it's a great idea to move everything to software and to use off-the-shelf hardware. That's in common, I think, across both. One of the things about NFV is if you look at it, the most important word in there is the F, the network function virtualization. NFV is really function-centric. And so what we're doing is we're virtualizing functions, and what it lets us do is implement what we did before with hardware appliances more efficiently and more flexibly in software. But ultimately, it's a new way of doing the same thing more efficiently, but we're essentially doing the same thing. SD-WAN is a kind of what I call customer network virtualization. Rather than thinking about things from a function point of view, we think about it from a customer's point of view, an individual customer, and what they want to achieve, what's their intent for their network. And instead of virtualizing the function, we're virtualizing their network and giving them a virtual network. And what this lets us do is deliver new capabilities to the customer, the ability to have an application-driven network where we're steering traffic and applying forward error correction and other techniques to deliver what they need on a per application basis, edge to edge. And in this sense, I think that NFV and SD-WAN or CNV are two different things. They're closely tied together. I think universal CPEs are a great host for an SD-WAN VNF, but they are coming at things from slightly different angles, or almost orthogonally. When you have a big data center, or whether you've got a VNF, you've got virtualization infrastructure, do you carve things up by customer or by function? So by function means you'd have a function that's multi-tenant, usable by many customers, or do you have one VNF per customer, or do you go with one VNF per function per customer? These are questions everybody's facing. So one thing I think it's interesting to think about, VMs and containers, they provide boundaries. The natural boundary, where should we put them? The natural boundary, I believe, is between customers. It lets you use virtualization to deliver comprehensible, provable isolation between customers. The functionality, using functions as a boundary, is in some senses artificial. Not all vendors agree. In fact, no vendors agree exactly where the boundaries of a particular function, like a firewall or WAN optimization VNF or a load balancer VNF, lie. And if we're going to make each of those things multi-tenant, we're solving the multi-tenant problem many times over when it's already solved for us in the hypervisor in the virtualization environment. The advantages of partitioning by customer is that every customer can run a different release, so that if there's a bug, you can upgrade one customer without worrying about what happens to all the others. If you have a customer who wants a advanced feature, you can give them that without having to test it for every single other customer. In fact, not only can you run different releases from the same vendor, you can run different vendors' stacks. And I think if we think about how we use virtualization, not just for virtualizing functions, but for virtualizing networks by customer, you can build carrier networks that have mass customization. So every enterprise gets exactly the network that they want. And this picture ends up looking something like this, where every customer has a different combination of VNFs. Some of the VNFs span multiple functions. Some overlap individual functions. But each customer is getting exactly what they need. And I think a lot of the groundwork for this type of network is being laid with NFV. But it is, I think, very interesting to think about, what do we do function-based? What do we do customer-based? I know my viewpoint might be a little bit heretical, but I wanted to kind of prompt people to think, where does virtualization help? And how can we leverage it to deliver more to the enterprise? So this is the last slide. And I want to round out by talking again, reminding you that SD-WAN, where we've got to get to, it's a self-driving WAN. And I talked to you today about 4 different ways we're applying AI and machine learning today. It's the beginning of a journey. I'm no way saying that we've solved the problems. There's a lot for us to continue to work on. But I think that the future of networking is all about how do we make our network self-driving, and how do we best leverage software and virtualization to deliver what enterprises want.